Okay, so we're looking at now what happens when we put a charge into this magnetic field. So instead of previously we were putting wires in the magnetic field, now we're just going to go ahead and put just a single electron or a single proton. Now this is kind of like the more sensible starting point, because actually it is the movement of the electrons in the wire that have the velocity that causes this. The protons stationary, so they don't experience the same force according to FSBIL. So magnetic field set up. This time I'm just going to fire like an electron into it. Now electrons, so I'd probably have to have some sort of like accelerating, some negative plate or something here to accelerate it away. Or if I wanted to fire a proton in, I'd probably have a positive plate set up, or just give them the velocity and allow them to travel through it, speed them up somehow. And I'll talk about how you can speed them up, because that's this thing here. So if I put my electron in, I should point out that I'm doing this like the paper is horizontal for me on a table, and the camera's above. So I'm kind of like, when I say it's going up, it's because it's going up. I guess it's like coming towards your screen. It depends on whether your laptop screen or your phone screen is horizontal or vertical. One of the big skills in this, and one of the reasons why this topic I think is tricky, is because they have these 2D representations of a 3D situation that they expect you to be able to interpret. And often the diagrams are tricky. It's hard to draw things coming into a page. I'll go through this kind of dot and cross notation for in and out of the page. They do that. They don't expect you to know that. They do explain that though if it's happening. So my magnetic field is going from north to south. Fleming's left-hand rule is going to tell us the direction of the force. And it goes from north to south. For the electron, and this is often tricky. You have to think about this. I have to think about this, because the electron is moving opposite in the direction of what we would say current, because current goes from positive to negative. So the way a proton would move. So my second finger for current is going to go in the opposite direction to the electrons moving. So my thumb is thoroughly pointing upwards or towards you, and so that means this electron is going to move up or towards you, right? Which is hard to draw. Yeah, it's hard to say it's going to go up. This proton, however, essentially the field has remained the same, which often is the case because the magnetic field is often something that's fixed, but this current is now that way. So this proton is going to move down, right? So it's going to go down into the page, into the desk for this 3D situation. Slightly easier with my model, where you could just say, well, if I fire an electron in here, the electron's going to go in there and then it's going to come up. If I fire a proton in there, the proton would go in there, it would experience a force, it would go down out of the model. But tricky when it's a 2D visualization of it. Now, the interesting thing comes if we look at our magnetic field, not like that, north and south, but like this, north and south. So if my model is kind of like, instead of being like this, it's kind of like that. It's difficult to use the model for that. So we represent this. These crosses represent field lines into the page. So first finger field. So there's a kind of north pole up here where you are and a south pole somewhere below. And the field is going down. So if you can imagine the field lines just traveling down. Into the page, towards you, out of the page would be just a dot, right? This is into the page. So if I put my electron in here, yeah, and I give it a velocity, as soon as it enters this magnetic field, it's going to experience a force. And I use Fleming's left-hand rule to work out the direction. So first finger field into the page, second finger current, which is the opposite direction the electron's moving. So it experiences a force here. The force is always perpendicular to the velocity because of Fleming's left-hand rule. Now, perpendicular force to the velocity vector isn't going to cause it to accelerate its speed. It's not going to get faster. What's going to happen is it's going to change direction. Its acceleration is going to be in moving of that velocity vector. The force in this direction is going to cause the velocity vector to curve around that way. So if I look at the particle, initially it's like that. If I look at it a little bit later, that force is going to cause the velocity vector to swing round. It's going to change direction. And now, if I put my finger, try and work out the new force, well, yeah, it's still perpendicular. I've had to move my second finger around because the velocity vector has changed direction, but it's still perpendicular. Then we go again. Still perpendicular force. And you can see what's happening to this particle. Because this force is always perpendicular to the direction of motion, the particle actually undergoes circular motion, right? It's going to move in a complete circle. Any negative particle that you put in here is going to move in a circle, yeah? Because circular motion. If it was a positive particle, it would still move in a circle. It's just the circle would be in the opposite direction. Now, and this is called circular. This is circular motion. Now, the equation for this, F, force, is equal to B, which is the same magnetic field strength, times the charge of the particle times the velocity. So it's a slightly different equation. It is the same as F is BIL. We just change we do a bit of like twiddling of it. And this, because it's circular motion, because this force is always towards the center of the circle, always perpendicular to the velocity vector, just like for the moon orbiting the Earth, the moon is fixed in circular motion because the force of gravity of the Earth is always perpendicular to the velocity vector of the moon at any given point. Because of this, we say F is BQV is equal to mv squared over r. So it goes all the way back into that circular motion topic from paper 1, from paper 2, at the start of year 13 or the end of year 12. Now, this though is not a very nice equation. We've got v twice, so we say BQ equals mv over r. So you can see here the velocity and the radius of the circle are going to be directly proportional to each other, because if you double the velocity for the same particle charge, same magnetic field strength, same mass, you're going to have double the radius. And that's used in this cyclotron and this velocity sector. So for the cyclotron, what you're doing is you shove your electrons in here. You have a little negative and positive electric field here. So initially, if you have an electron here, you have the electric field set up so it's positive at the front. That accelerates the particles. That does nothing but accelerates them. It makes them move faster because they're moving in that direction and the force is in the that direction, so they're going to get faster. But then as soon as they hit the magnetic field, they don't go faster anymore. The force on the magnetic field is acting perpendicular. They've left the electric field, and so they're going to spin around, right? Then they flip this. So this flips. So now it's negative there, positive there. So now they accelerated down here. Now they're going faster, right? Every time they go through this electric field, they get faster. Their velocity increases. And now, so because the velocity increases, the radius is going to be bigger. So we get a bigger radius. Then we flip this again. Now it's positive, back to positive and negative. They're going to get faster here. It's going to be a bigger radius here. They're going to get faster at this bit. We flip it, the faster, bigger radius. Flip it again. They get faster there. So then they do a bigger radius here. Flip it again, faster there, bigger radius. All the time this particle is getting faster and faster until eventually, I've done it the wrong way around. Eventually they fire them out, right? They fire them out when they've reached the radius required, and the radius required will be the velocity they require of their particles, and then, maybe they use them for all sorts of things. But that's how a cyclotron works. It uses the magnetic field to curve it round, and the electric field, an alternating electric field, to accelerate it in the gaps between these two. They're called Ds. It's a type of particle accelerator. This is the application that's quoted on the specification. The other application that comes up a lot, because it allows them to link magnetic fields and electric fields, is this idea of a velocity sector. So the velocity selector, if I have a magnetic field going into the page, then any charged particle, so if I have an electron, or let's just say proton, because I've used electrons a lot, it doesn't really matter. If I have a proton going in here, right, the proton is going to experience a force up, right? So this proton is going to experience a force because of the magnetic field. When it's in the field, right, this proton experiences a force up, force magnetic, which is going to be equal to BQ times the velocity. Now, it's also going to experience an electric force, but the electric force is going to act down because of this electric field it's in as well. Now, the electric, it goes back to the electricity part of it. Now, when the force on the magnetic field, force because of the position in the magnetic field, equals the force in the position of the electric field, the forces are balanced. It's not going to curve around. It's just going to come straight out. But that will only happen at specific velocities. Now, if the velocity is bigger, it's going to experience a greater magnetic field, and so it will curve up. If the velocity is smaller, the magnetic field will be weaker, the electric field will be stronger, and it will move towards the plate. So it allows you to put in a load of protons at different velocities, and only the ones that have the perfect velocity for your specific magnetic field and electric field will leave out the end. So that was tricky. Next bit is now going to talk about how we create electricity, which is very important.